Imagine an adhesive, right? Like a tape that is strong enough to hang a 290-pound NFL linebacker from your ceiling.
Which is a pretty terrifying image, honestly.
Yeah, I mean, it's a lot of weight. But now imagine that this exact same adhesive leaves absolutely zero sticky residue behind when you pull it off.
Right.
And it works perfectly in the total vacuum of outer space. And on top of all that, it just cleans itself of dust and dirt without a single drop of water.
It sounds like magic.
It really does. If you heard those specs, you might think, we were talking about some highly classified, multi-billion-dollar synthetic metamaterial being cooked up in like a subterranean DARPA lab.
Yeah, some secret government project.
Exactly. But you would be wrong, because you have probably seen this exact technology just hanging out, quite literally, on your living room window.
It's true. The natural world just has this way of making our most advanced human engineering look, well, almost primitive by comparison.
So true.
I mean, we see a tiny gecko effortlessly scurrying up a perfectly smooth pane of glass, and our brains immediately try to rationalize it using macroscopic concepts that we understand, like suction cups or sticky sap or maybe microscopic hooks.
Because that's how things stick in our everyday lives.
Exactly. But the reality of what is actually happening under those toes is so much stranger. It is a biological machine that is defying the macroscopic laws of friction by directly manipulating quantum-level physics.
And that impossible paradox is exactly what we're getting into today. So, welcome to this deep dive. Today, we are taking a massive stack of research and distilling it down for you.
And it's a really good stack today.
Oh, it's a genuinely fascinating collection of academic papers we've got on the table. We're looking at groundbreaking research from UC Berkeley, Stanford University, the Carnegie Mellon University School of Computer Science, and even some material straight from NASA's Jet Propulsion Laboratory.
It's just a beautifully interdisciplinary stack of research. To truly understand this, we are pulling threads from evolutionary biology, paleontology, quantum physics, contact mechanics, and even aerospace engineering.
Just casually mixing quantum physics and lizards.
Right. And they're all zeroing in on this one specific, totally mundane miracle that we just take for granted every time we see a lizard on a wall.
Okay, let's unpack this. Our mission for you today is simple, yet incredibly complex. We are going to decode the biological and physical secrets of gecko foot nanostructures.
Van der Waals adhesion.
Yes. We want to understand how this tiny creature utilizes an evolutionary trick to stick to anything, and how that exact same 100-million-year-old trick is currently inspiring cutting-edge robotic technology bound for the International Space Station.
Which is just wild to think about.
I know. So I'm here to ask the questions, try to translate the heavy jargon into English, and almost certainly get my mind blown.
And my goal is to help synthesize this incredibly dense biophysics into clear, aha moments for you. We're going to take the microscopic math and really ground it in the real world.
Let's start at the very beginning then, because before we can even touch the space robots, we have to look at what nature has already perfected.
Yeah, the biological blueprint.
Right. And I have to assume this wasn't an overnight biological success story. If we are looking at the evolutionary timeline of the gecko, how far back does this sticky foot technology actually go? Like, are we talking a few million years?
Oh, considerably older than that. If we look at the phylogenetic tree, the suborder of lizards that includes geckos, which biologists call Geckota, that diverged from other lizard clades roughly 200 million years ago.
200 million years. Okay, so
Yeah.
we are talking about the Triassic period. Like, dinosaurs are just barely getting started, and the ancestor of the gecko is already branching off.
Yes.
But did they have the sticky feet back then? Or did that come later?
Well, that is where the paleontology comes in. And the sources provide this stunning piece of evidence. Paleontologists have discovered fossil specimens of an ancient species called Gecko balticus.
Gecko balticus. Catchy.
Right. And these aren't just your standard bone impressions in a rock. These specimens were found trapped and perfectly preserved in Baltic amber.
Oh, wow. Like the mosquito from Jurassic Park?
Very much like that, yeah. Amber preserves soft tissue details that stone fossils just can't hold on to.
Because it's tree resin that hardened.
Exactly. And when researchers examined the feet of Gecko balticus, which date back at least 100 million years, they found that these highly sophisticated, fully formed subdigital toe pads, the exact adhesive structures we are studying today, they were already present.
Wait, really? Yes.
They were fully functional back in the Cretaceous period.
That is wild. While a Tyrannosaurus rex was roaming around, there was a little gecko running up a prehistoric tree trunk using the exact same quantum physics we are trying to reverse engineer today.
It really puts our human engineering struggles into perspective, doesn't it? Nature had this solved 100 million years before humans even existed.
It's humbling for sure.
And what's even more fascinating from an evolutionary standpoint is that this complex adhesive pad system, it wasn't just a one-time genetic lottery win.
What do you mean?
Well, the phylogenetic analyses reveal that this trait has been subject to multiple independent evolutionary gains and losses across different lizard lineages over millions of years. It is a prime example of convergent evolution.
Convergent evolution. Okay, that's when entirely different species evolve similar traits
Yeah,
independently, right? Because they are trying to solve the exact same environmental problem.
exactly.
Like how birds and bats both evolved wings, even though they aren't closely related at all.
That's a perfect comparison. The research highlights the Anolis lizard, often called the Carolina anole, as a great example of this.
Okay, the anole, I've seen those guys around.
All right, they're very common. The anole clade convergently evolved subdigital toe pads that function on the exact same fundamental physics as the geckos. But they are vastly different in their complexity.
How so? Like, is one better than the other?
Well, the anole's adhesive hairs are much simpler. They are unbranched, much shorter, only measuring about 20 micrometers in length, and they exhibit what we call a single-tiered compliant mechanism.
So they're kind of basic?
Yeah, they get the job done for a lightweight lizard, but they're relatively basic. The gecko, on the other hand, specifically the Tokay gecko, which is the primary subject of these engineering papers, has a highly branched, multi-tiered architecture.
So the anole has the base model sedan, and the gecko has the fully loaded luxury sports car version of Sticky Feet.
I love that analogy, yes.
Let's actually pop the hood on that luxury sports car then. I want to walk down the microscopic rabbit hole of the gecko's foot from the macro level that we can just see with our eyes all the way down to the nano level.
It's quite a journey.
The sources describe a very specific structural hierarchy, and we really need to visualize it.
Let's start at the macro scale. If you ever get the chance to look at the bottom of a gecko's foot through a pane of glass, you'll see these expanded digital pads on the toes. These broad pads are called scansers.
Okay, stancers, I'm picturing them. They look kind of like fleshy horizontal ridges or overlapping flaps running across the bottom of the toe, right?
Right. Now we take out a magnifying glass and zoom into the mesoscale. Those scansers are lined with rows of lamellae, which are essentially the overlapping plates or scales that make up those ridges you just described.
Okay, scancers, then lamellae.
But the real magic starts when we bring out the electron microscope and cross into the microscale. Those lamellae are not smooth skin. They are covered in a dense microscopic forest of hair-like structures called setae.
Setae, S-E-T-A-E.
Correct. And the density is just staggering. A single foot of a Tokay gecko possesses nearly 500,000 of these setae.
500,000 on one tiny foot.
Yeah. And to put that physical scale into perspective for you, each seta is between 30 to 130 micrometers long and only about 1/10 the diameter of a single human hair.
Okay, so I am imagining 500,000 hairs on one foot, with each hair being 10 times thinner than the hair on my head. That alone is incredibly complex. But we aren't done zooming in yet, are we?
Not even close. Now we cross the boundary into the true nanoscale.
Buckle up.
If you follow one of those microscopic setae to its very tip, you'll see it doesn't end in a single point. It splits and branches out, kind of like the canopy of a tree, into hundreds, sometimes thousands, of incredibly tiny terminal projections. These are known as spatulae.
Spatulae, like the spatula you use to flip pancakes in the kitchen.
Named for that exact reason, actually. They terminate in these incredibly flat, triangular, scalpel-like tips. And these spatulae are unfathomably small.
How small are we talking?
We are talking about structures where the tip is just 0.2 to 0.5 micrometers wide. That translates to roughly 200 nanometers on the flat side and 10 to 30 nanometers thick.
Okay, just so we can wrap our heads around this. We went from the toe pad to the ridges on the toe, to a microscopic hair on the ridge, to 1,000 nanospatulas on the end of that single microscopic hair.
It's a fractal geometry of stickiness.
I was reading through the source material, and I found a statistic that genuinely made me pause and reread it, just to make sure I wasn't crazy. A single Tokay gecko has approximately 1 billion spatulae on a single foot.
1 billion, yes.
1 billion nano contact points. points.
It is an absolute masterpiece of biological structural engineering.
But structure is only half the battle, right? I mean, I can build a perfectly structured bridge out of wet cardboard and it's still going to collapse. The mechanical performance of this foot has to depend on what it's actually made of.
Without a doubt, the material composition is critical. The researchers use techniques like electrophoretic and microbeam X-ray diffraction analyses to study this.
Stop right there. Microbeam X-ray diffraction analysis is a mouthful. I'm assuming that's basically bouncing X-rays off the foot to see the exact molecular blueprint of the proteins.
That's a very accurate translation, yeah. By observing how the X-rays scatter, they can map out the crystalline structure of the material.
Okay, and what did they find?
What they found is that the structural core of the settle stalk is composed of polymerized, low molecular weight beta-keratin, and it is lightly coated in a very thin lipid envelope containing both polar and nonpolar lipids.
Okay, I have a major point of pushback here. Beta-keratin, I know that word. Isn't beta-keratin the exact same protein that makes up bird feathers, reptile scales, and, like, human fingernails?
It is the exact same base material, yes. Beta-keratin is a highly structured, naturally occurring protein.
Okay, but my fingernails definitely do not stick to walls. If I press my fingernail against my living room window as hard as I can, absolutely nothing happens. I just leave a smudge.
Right.
So how is it physically possible that a billion tiny fingernails suddenly become the strongest natural adhesive on Earth?
That is the perfect question. And it brings us to one of the central paradoxes of the entire Gecko adhesive system, the paradox of material stiffness.
Okay, explain this paradox.
Beta-keratin is incredibly stiff. In material science, we measure the stiffness or elasticity of a solid material using a metric called Young's modulus.
Young's modulus, got it.
The Young's modulus of Gecko Setae beta-keratin is estimated to be between 1.4 and 1.6 gigapascals.
Gigapascals, I don't know the exact math on that, but the prefix giga tells me it is very, very rigid.
It is extremely rigid. To give you a comparison, a soft rubber band might have a Young's modulus of around 1 megapascal.
Wow. So this beta-keratin is over 1,000 times stiffer than a rubber band.
Exactly. Now, under normal evolutionary circumstances, having a material this stiff on the bottom of your foot is highly advantageous. It is highly resistant to wear and tear.
Which is exactly what an animal running across rough bark and jagged rocks needs to survive. You don't want soft, mushy feet.
Right. But a material that's stiff is fundamentally incapable of acting as an adhesive. It simply cannot deform and squish down to create the intimate surface contact area required to stick to anything.
So we have billions of microscopic, rigid fingernails on a gecko's foot. How does that translate into an incredibly strong, glueless adhesive?
It's a mystery that baffled scientists for a very long time.
To understand the true physics of the stick, I think we first need to look at all the theories that scientists got completely wrong over the last century. Because before they figured out the quantum physics, they had some pretty wild guesses.
It really is a graveyard of debunked hypotheses. For decades, naturalists and early biologists observed geckos scurrying up walls, and they just threw out educated guesses based on macroscopic mechanics.
What was the first big guess?
Well, in 1934, a German scientist named Dellert hypothesized that it was micro-interlocking.
Micro-interlocking, meaning the feet acted like microscopic hooks catching onto tiny bumps on the wall. Sort of like a biological Velcro.
Exactly. The logic was actually quite sound for the time. The idea was that no natural surface, like a rock or a tree, is perfectly smooth at the microscopic level. They are full of microscopic pits and crevices.
Right.
So Dellert thought these microscopic hairs were just acting like tiny grappling hooks.
It makes sense intuitively, so how is it debunked?
It was debunked relatively simply when researchers observed geckos effortlessly climbing perfectly polished glass.
Oh.
Yeah. Polished glass has a surface roughness that is smaller than the tips of the spatulae. There are literally no irregularities or crevices large enough for a physical hook to catch on.
And yet the gecko climbed it without any issue.
Exactly. So the Velcro theory was dead.
Okay, so Velcro is out. What do they try next?
Suction. People thought, okay, if it's not hooks, maybe the toes act like hundreds of thousands of microscopic plunger cups. When the gecko steps down, it forces the air out, creating a vacuum seal on a microscopic level.
Honestly, given how weird nature is, that doesn't sound entirely crazy.
It didn't. But it was famously debunked by placing geckos in a vacuum chamber.
Wait, they put a lizard in a vacuum chamber? That must have been a very bizarre day in the laboratory.
Obviously, they had to be careful with the animals, but yes. They tested the adhesion in an environment where all the air was pumped out.
And suction relies entirely on the differential in air pressure.
Exactly. If there is no air, there is no air pressure to hold a suction cup against a wall. It is physically impossible for suction to work at a total vacuum.
And yet, in the vacuum chamber, the geckos could still stick to the walls just fine.
Just fine.
All right. So we've ruled out tiny grappling hooks, and we've ruled out microscopic plungers. What was the next theory to fall?
Electrostatic attraction.
Okay, like when you take a latex balloon, rub it on your hair, and then stick it to the ceiling. Did they think the gecko was generating static electricity as it ran?
That was the exact theory. The friction of the hairs against the surface was thought to generate a massive static charge. But scientists managed to eliminate this possibility using X-ray bombardment.
Wait, how do X-rays debunk static electricity?
When you flood a chamber with X-rays, the high-energy radiation ionizes the air molecules inside. It creates a cloud of free-floating positive and negative ions.
Okay.
If a surface has a static electric charge, those free ions in the air are immediately attracted to it, coating the surface and instantly neutralizing the static charge.
Ah, I see.
So if the gecko was relying on static electricity, flooding the space with X-rays would instantly cause it to fall off the wall.
And it didn't.
It did not. The geckos adhered perfectly, completely unbothered by the ionized air.
Man, they tread everything. And I'm assuming we also ruled out some kind of biological glue or sticky secretion, like
Yeah.
a tree frog or a slug.
Yes, quite easily and quite early on. Detailed anatomical studies and histological sectioning of the gecko's toes confirmed that there are simply no skin glands on the feet of these lizards.
Not at all.
None. They secrete no fluids, no natural glues, no mucus. It is a completely dry, solid-state adhesive.
Okay, this is where it gets crazy. If it's not hooks catching on bumps, it's not suction cups, it's not static electricity, and they aren't sweating glue, what is left? It feels like we've exhausted all the physical ways things stick together.
What is left is a phenomenon known as van der Waals forces. And to understand it, we have to leave biology behind and cross over into quantum physics.
Okay, I definitely remember hearing the term van der Waals forces in my high school chemistry class, but I am going to need a serious refresher. Give me the accessible version. What exactly is a van der Waals force?
Van der Waals forces are intermolecular forces. They are the distance-dependent attraction between individual atoms or molecules.
Okay.
The crucial thing to understand is that unlike ionic or covalent bonds where atoms are permanently sharing or stealing electrons from each other to stick together, like in a molecule of water, van der Waals forces do not involve any chemical bonding whatsoever.
Wait, if they aren't bonding chemically, how are they attracting each other?
It all comes down to the unpredictable quantum movement of electrons. Electrons are constantly orbiting the nucleus of an atom in a sort of probability cloud.
Right, they're zipping around constantly.
Exactly. And at any given fraction of a nanosecond, purely by chance, the electrons might happen to be slightly more clustered on one side of the atom than the other side.
Okay, and electrons have a negative charge.
Right. So for that tiny fraction of a millisecond, that clustering creates what we call a temporary instantaneous dipole, meaning one side of the atom is suddenly slightly negative and the other side is slightly positive.
And because atoms are packed tightly together in solids, that sudden slight charge must affect the atom right next to it, right? Like a tiny magnet.
Exactly. That temporary dipole induces a corresponding dipole in the neighboring atom. The slightly negative side of atom A pushes the electrons in atom B away, making the near side of atom B slightly positive.
Oh, I see.
And for a fleeting, incredibly brief moment, those opposite charges attract each other.
So they basically blink into existence as tiny magnets, attract each other, and then blink out as the electrons keep moving.
That's a great way to visualize it. Now, on a macroscopic scale, like two regular objects touching, these forces are incredibly, almost unimaginably weak. They're easily overpowered by just about every other force in nature.
Which is why my hand doesn't get quantumly stuck to my coffee mug.
Precisely. And the most important detail is that they only work at extremely close distances, what physicists call an atomic gap distance. We are talking about a distance of roughly 0.3 nanometers.
0.3 nanometers. A single sheet of paper is, what, 100,000 nanometers thick. So 0.3 nanometers is literally the distance between individual atoms.
Yes, for a van der Waals force to work, the two surfaces basically have to be physically touching at the atomic level.
The atoms of the gecko's foot and the atoms of the wall have to be intimately, perfectly mated together.
They do. And this brings us right back to the paradox we discussed a few minutes ago regarding the stiffness of the beta-keratin. It is known in material science as the Dahlquist criterion paradox.
Right, because the beta keratin is 1,000 times stiffer than rubber. Let's break down this Dahlquist criterion. Why is it a paradox?
Let's think about how humans make adhesives. If you want to manufacture a piece of conventional tape, what the industry calls a pressure-sensitive adhesive or PSA, like Scotch tape or duct tape, it has to be soft, gooey, and viscoelastic.
Okay.
The Dahlquist criterion is an established rule of thumb that states for a material to be naturally tacky, its elastic modulus must be under 100 kilopascals.
So it has to be soft enough to literally smush down and conform to the microscopic hills and valleys of whatever surface you are pressing it against.
Exactly. Think about a wad of chewing gum. If you press it onto a wooden desk, it oozes and flows into the microscopic grain of the wood. It gets perfectly close to the atoms of the wood, and it sticks.
But remember, the beta keratin of the gecko's foot has a modulus of 1.4 gigapascals.
Yes. It is 3 orders of magnitude too stiff to satisfy the Dahlquist criterion. If you took a solid block of beta-keratin and pressed it against a wall, the stiff block would just bridge across the highest microscopic peaks of the surface, leaving massive air gaps everywhere else.
So it would never get within 0.3 nanometers of the surface to engage those van der Waals forces.
Right. It would never be close enough.
It's like trying to get a Lego brick to mold into the shape of a golf ball. It just rests on the bumps. So how does the gecko solve this? How does a 100-million-year-old lizard make a material as rigid as a fingernail act like soft chewing gum?
The biological solution is a brilliant feat of mechanical engineering called contact splitting.
Contact splitting. Okay, let me try out an analogy here to see if I'm understanding this correctly.
Go for it.
Let's say you have a bumpy, uneven cobblestone floor. If you try to sweep that floor by dragging a solid, flat block of wood across it, the wood just clatters across the very top of the highest cobblestones. It bridges the gaps, and it misses all the dirt in the cracks.
Right, because the wood is too stiff to conform to the floor.
Exactly. But if you take that exact same block of wood, that exact same stiff material, and you carve it into a fine bristled broom suddenly, those millions of individual flexible bristles drape over the stones. They fall down into every single microscopic nook and cranny.
That is a phenomenal analogy.
The material didn't get softer, but the structure allowed it to conform.
That is exactly what contact splitting is.
Right.
By dividing a single continuous contact area into an array of millions of independent nanoscale subcontacts, the spatulae, the gecko solves the stiffness problem.
Wow.
The bulk material of beta-keratin remains a rigid 1.4 gigapascals, but because it is split into these incredibly fine microscopic tree-like branches, the effective elastic modulus of the entire subtle array drops dramatically. It drops to roughly 100 kilopascals.
Which is exactly the number required by the Dahlquist criterion. By splitting the hairs a billion times, the rigid fingernail functionally becomes as tacky and compliant as chewing gum.
It is brilliant, and researchers can actually model the mechanics of how these individual spatular contacts deform and adhere using advanced contact mechanics theories, specifically the JKR and DMT models.
JKR and DMT. I'm going to need you to unpack those acronyms for me.
Of course. JKR stands for Johnson Kendall Roberts, and DMT stands for Durjagan Miller Toporov. They are fundamental mathematical models used in tribology, which is the study of friction and wear in contact mechanics.
Okay, so what do?
They describe exactly how two elastic surfaces deform when they are pressed together and pulled apart.
So there are math equations that predict how squishy things act when they touch.
Essentially, yes. The JKR model specifically accounts for strong adhesive interactions like the van der Waals forces we've been discussing and the elastic deformations within the contact zone.
And this applies to the gecko foot.
Yes, it's highly applicable to larger, more compliant contact geometries, which perfectly describes how the gecko's Setae array functions as a macroscopic whole. The structural compliance of these tree-like branches allows the stiff keratin fibers to bend, shear, and drape over the surface roughness, establishing that intimate nanoscale contact.
And because there are 1 billion of these spatulae perfectly draping over the atomic surface of the wall, those tiny, incredibly weak, temporary van der Waals forces suddenly add up to something absolutely massive.
The cumulative force is staggering.
I want to talk about exactly how staggering, because the sources detail an experiment that completely blew my mind. We were talking about researchers at the Carnegie Mellon University School of Computer Science in UC Berkeley.
Right, the single Setae experiment.
Yes. They actually managed to isolate and measure the adhesive force of a single Setae, How on earth do human beings measure the pull of one microscopic hair that is a tenth the width of a human hair?
It was an engineering marvel in and of itself, just to run the test. To measure something that small, you can't just use a tiny spring scale. They had to design a custom dual-axis microelectromechanical systems force sensor. We call it a MEMS cantilever.
A MEMS cantilever. So we are talking about a microscopic diving board built on a computer chip.
That's a great way to picture it. It was fabricated on single crystalline silicon wafers. It was equipped with two independent force sensors, capable of measuring forces both parallel and perpendicular to the surface simultaneously. It used a piezoresistive readout.
Piezoresistive meaning that the electrical resistance of the material actually changes as it physically bends.
Correct. As the microscopic diving board bent under the pull of the gecko hair, the electrical current passing through it changed. By measuring that change in current, they could calculate the force with extreme precision. We're talking about measuring forces down to about 5 nanonewtons.
The delicacy required for this is insane. So some poor grad student had to isolate a single hair from a gecko foot, glue it to the tip of an insect pin using 5-minute epoxy under a high-powered microscope, and then touch it to this microscopic silicon diving board.
That's pretty much exactly how it happened.
What were the results?
What's fascinating here is that the empirical measurements blew the theoretical models out of the water. They found that a single setae is vastly more effective at adhesion than anyone predicted. A single setae produced an average maximum adhesive force of 194 micronewtons.
194 micronewtons. Okay, let's scale that up so we can actually comprehend the power of this evolutionary design. Let's do the math on a whole gecko. If a tokay gecko utilized all 6.5 million setae on its feet simultaneously,
If we assume ideal conditions, where every single one of those 6.5 million hairs engaged perfectly flat against the surface at maximum force, that single tiny gecko could theoretically support a shear load of roughly 130 kilograms.
130 kilograms, that is 286 pounds. A 290-pound professional NFL linebacker could be suspended from the ceiling by a lizard that weighs a few ounces.
Yes.
The physical strength of this quantum bond is terrifying.
It is immense. Now, in reality, geckos only lift about 2 kilograms, or roughly 4 pounds, with their front feet.
Why the huge difference?
Because on a rough natural surface like a tree, it's statistically impossible for every single microscopic hair to be perfectly aligned and engaged at the exact same time. There are always gaps. But the sheer potential force is what makes this system so robust.
Which leads us to a massive practical problem. Having the adhesion force to hold up a football player is an incredible parlor trick, but it is a biological death sentence if the gecko can't let go to take its next step.
Right.
If I wrap the bottoms of my shoes in industrial duct tape, I'm not going to be able to run up a wall. I'm just going to be hopelessly stuck to the floor. How do geckos run so fast they can move meters per second without permanently gluing themselves to the ceiling with every step?
This was the next great mystery that researchers had to solve. And what they discovered is that the gecko foot is not just a passive, dumb piece of tape. It is a highly sophisticated, directionally controllable adhesive system.
Let's talk about the art of the peel. How exactly do they turn the stickiness off?
To understand how they turn it off, we first have to understand how they turn it on. The researchers using that tiny MEMS silicon diving board made a vital discovery regarding two concepts they called preload and drag.
Preload and drag.
They found that if you take a setae and push it directly straight down perpendicularly into a surface, it produces almost no adhesion at all. We're talking less than 0.3 micronewtons of force.
Wait, really? If you just poke the wall straight on with the toe, nothing happens? It doesn't stick?
Correct, because in their default resting state, the stalks of the setae are angled away from the pad. They are naturally non-sticky. But if you apply that tiny perpendicular, push the preload, and then you pull the setae parallel to the surface.
The drag.
Yes, the drag. If you drag it just 5 micrometers along the surface,
5 micrometers. That's entirely imperceptible to the human eye.
it is a microscopic shift. But dragging it that tiny distance causes the adhesion force to increase enormously. It spikes over 600-fold.
Wow. Okay, so dragging the foot mechanically forces the branched spatulae to lay perfectly flat against the surface, aligning all those billions of atomic dipoles to trigger the van der Waals forces. It's like locking a mechanism into place.
Exactly right. The drag physically aligns the asymmetric tips of the spatulae with the surface. But the absolute genius of the system is that this process is entirely reversible based solely on the angle of the hair.
The critical angle of detachment.
Precisely. The researchers found that the van der Waals bonds are incredibly strong when pulled along the surface. But if the angle between the settle shaft and the surface increases past a critical boundary, specifically about 30 to 30.6 degrees, the intermolecular bonds fracture,
And the stickiness goes away.
the adhesion instantly drops to zero.
Here's where it gets really interesting. I am marveling at the description of this in the source text. When a gecko runs, it doesn't just lift its foot straight up like a human lifting a boot out of the mud. It performs a specific behavioral movement called digital hyperextension.
Yes.
The paper describes it as uncurling their toes like an inflatable party favor. I love that imagery.
It's very accurate visually. When they want to detach their foot, they don't pull up. They roll their toes upward and backward, starting from the tip of the toe and rolling back toward the base of the foot. Distal to proximal.
Let me make sure I'm wrapping my head around this. The gecko is actively controlling the quantum stickiness with every single microscopic step. It's not just a passive sticker, it's a mechanical switch.
It is a perfect mechanical switch. And here's where the mechanics get incredibly elegant.
Yeah.
By peeling the toe backward, the gecko is manipulating stress at the microscopic level.
Okay, how does that work?
When the toe is engaged in pulling the gecko's weight, the stress is distributed as a uniform shear stress across the entire pad. It's sliding force. But when the gecko hyperextends the toe and curls it up, it changes that uniform shear stress into a concentrated tensile stress right at the trailing edge of the spatular contact patch.
Tensile stress meaning it's pulling straight up, perpendicular to the bond rather than sliding.
Yes. And while van der Waals forces are incredibly strong against shear force, they are highly susceptible to being peeled via tensile force. By rolling the toe, the gecko causes a cascading peel.
Like unzipping a jacket.
Exactly like the teeth of a zipper opening. The spatulae don't all detach at once. They detach a few at a time, row by row. Digital hyperextension ensures that only a microscopic fraction of the total settle array is detaching at any specific millisecond.
Which means the actual muscular force the gecko needs to exert to unstick its foot is virtually zero. It's peeling the tape at the perfect angle, so it offers no resistance.
That's the beauty of it. It attaches with the strength to hold the 290-pound linebacker, and it detaches with the effort of lifting a feather. It is the ultimate controllable, reusable adhesive.
Okay, my mind is thoroughly blown by the concept of a mechanical quantum switch, but we have another paradox to address, a massive one. Let's go back to my Scotch tape analogy.
Okay.
If I take a piece of Scotch tape and I accidentally drop it sticky side down on my kitchen floor, it is ruined forever. It is instantly covered in dust, dog hair, and crumbs. It will never stick to anything ever again.
That's true.
But geckos live in the dirt. If a gecko's feet are sticky enough to hold hundreds of pounds and they are constantly walking on dirt, sand, and flaking bark, why aren't their feet just massive, useless, matted balls of dirt?
It is the paradox of the sticky yet clean foot. It's a brilliant question that stumped scientists for a long time. As you pointed out, most conventional adhesives lose their tackiness instantly upon contamination.
Yep.
But geckos require absolutely no active grooming. You never see a gecko sitting on a branch picking dirt out from between its toes with its mouth. Their feet are completely self-cleaning.
When I hear the term self-cleaning in nature, my mind immediately goes to lotus leaves. I know that lotus leaves have microscopic bumps that make water bead up and roll off, taking the dirt with it. Is the gecko foot doing something like that?
That is a very common assumption, but no, and that is a crucial distinction to make. The lotus effect relies entirely on superhydrophobicity and rolling water droplets to physically wash the surface clean. Geckos, however, can clean their feet bone dry.
Bone dry.
Yes, they do not need rain or dew to wash the dirt away. The self-cleaning of a gecko toe is a passive physical property driven by two highly distinct mechanisms.
All right, I'm ready. What is mechanism number one?
Mechanism one is called static thermodynamic disequilibrium.
Okay, static thermodynamic disequilibrium sounds like something that would cause a warp core breach on Star Trek. We are definitely going to need to translate that.
It sounds intimidating, I know, but the physical concept is actually quite elegant. Let's walk through a scenario. Imagine a tiny particle of silica dirt gets stuck to one of the gecko's spatulae.
Okay.
When the gecko takes its next step and presses its foot down onto a clean wall, that tiny dirt particle is sandwiched perfectly between the wall and the gecko's spatula.
Right, it's trapped in the middle.
Exactly. Now, the physics of van der Waals forces dictate that the strength of the attraction is proportional to the contact area. The wall is a massive, relatively continuous surface. The spatulae are microscopic, sharply pointed triangles.
Okay, I see where this is going.
Mathematically, the energetic force attracting that dirt particle to the large surface of the wall is stronger than the cumulative energetic force attracting it to the few microscopic spatulae it's touching on the gecko's foot.
Wait, are you saying the dirt literally prefers the wall over the gecko foot?
From an energetic standpoint, yes.
Yeah.
Because of the highly divided geometry of the spatulae, there simply isn't enough surface area in contact with the dirt particle to hold onto it tightly. The wall has far more surface area, therefore a much stronger van der Waals attraction. So when the gecko naturally lifts its foot to take a step, the dirt particle just stays stuck to the wall. The gecko walks away clean.
That is wild. The dirt essentially unsticks itself because the wall acts as a better magnet for it. It gets outcomputed.
That's a perfect way to phrase it.
Okay, that makes sense for a flat wall, but what if they are walking on loose sand? What is mechanism number 2?
Mechanism 2 is dynamic inertial shedding. And this relates directly back to how the gecko walks, that rolling motion we discussed.
Digital hyperextension.
Yes. During the peeling action, the gecko is mechanically pulling on those stiff beta-carotene setae. As those hairs bend backward, they build up a tremendous amount of elastic energy, exactly like drawing back the string on a bow.
Okay, I think I see where this is going. It's like taking a plastic school ruler, holding it flat on a desk with half of it hanging off the edge, bending the free end down, putting a crumpled up piece of paper on it, and then letting it go to flick the paper across the classroom.
That's a perfect visualization. As the gecko keels its toe, the setae bend further and further until they reach that critical 30-degree angle, and then they let go. At that exact moment, the van der Waals bonds fracture, and the hair releases from the surface. Because it's made of incredibly stiff beta-carotene, it snaps back to its resting state incredibly fast. This rapid microscopic snap generates a massive inertial force at the very tip of the seta.
It acts like a microscopic catapult.
Yes, physically flicking any stubborn dirt particles right off the tip.
So they are literally flicking the dirt off thousands of times a second as they run. It's a rapid-fire dirt catapult. That is so cool. Now, earlier you mentioned a lipid envelope coating these hairs. Does the chemical makeup of the foot help with this self-cleaning process at all, or is it purely mechanical?
The mechanical catapult is the primary driver, but if we connect this to the bigger picture of the biochemistry, the lipid envelope plays a fascinating supporting role. The outermost surface of the spatulae is coated in a very thin layer of phospholipids and neutral lipids. Researchers notice that when a gecko walks across perfectly clean glass, it actually leaves behind a microscopic invisible footprint of these unbound lipids.
Like leaving greasy fingerprints on a sliding glass door.
Essentially, yes.
Yeah.
But it serves a vital evolutionary purpose. This lipid layer is designed to undergo what we call cohesive failure under high shear stress.
What does cohesive failure mean in this context?
It means that if the gecko's foot drags too hard against a rough surface, the lipid layer is designed to break apart and shed onto the surface, rather than the underlying structural beta-carotene tearing or snapping. It acts as a sacrificial dry lubricant.
Oh, that's smart.
It protects the delicate spatulae from mechanical friction damage, and by constantly shedding its outermost molecular layer, it also inherently prevents sticky substances from permanently bonding to the tissue.
It's like they have a biological Teflon nonstick coating mixed with tiny catapults. Nature is just showing off at this point.
It really is a supremely optimized system. We are looking at millions of years of brutal natural selection, operating relentlessly on the nanoscale to perfect a dry adhesive. Which brings us to the ultimate question for our species: how do we steal it?
Yes. Let's pivot to biomimetics and engineering. We have completely decoded this 100-million-year-old secret. We know the material is stiff beta-carotene. We know the mechanical trick is contact splitting. We understand the van der Waals forces, the 30-degree peeling angle, the inertial shedding. If we have the blueprint, let's just build it. Why don't I have a pair of Spider-Man gloves in my garage right now?
Well, understanding the physics is one thing. Manufacturing at the nanoscale is quite another. The engineering challenge is immense.
Really? With all our modern tech?
Manufacturing small, closely packed arrays that accurately mimic Gecko Setae tests the absolute limits of our current material science technology. We're trying to replicate a hierarchical structure that scales flawlessly from the millimeter down to the nanometer.
What are the specific hurdles? Why can't we just 3D print it?
3D printing simply doesn't have the resolution required for nanoscale spatulae. Researchers have had to try two main approaches. One is top-down lithography, where you take a bulk material and use chemicals or lasers to carve microscopic structures out of it, much like how computer chips are made.
Okay, and the other?
The other approach is bottom-up nanostructure synthesis, where you try to chemically grow the fibers from a substrate up, atom by atom.
What materials are we using for this, since I'm assuming we can't easily farm or print beta-carotene?
We've experimented with a wide variety of synthetics. Researchers have created polyurethane microarrays, they've used shape memory polymers, and there's been extensive work using carbon nanotubes.
Carbon nanotubes, those are super strong, right?
Incredibly strong, very rigid, and can be grown in dense, forest-like arrays, making them a very good candidate to mimic the contact splitting of Setae. Researchers have also created what are called annular wedge structures. They fabricate these using ultra-precision diamond cutting tools to physically mimic the asymmetrical triangular shape of the Gecko Spatulae.
Okay, so we are throwing diamonds and carbon nanotubes at the problem. Are these synthetic versions actually working? Do we have real-world applications yet, or is this still just lab experiments?
We absolutely have real-world applications,
Yeah.
and the progress has been remarkable. You have commercial materials like Gecko Skin, which was developed by researchers at UMass Amherst.
Skin, good name.
Right. They took a slightly different approach. Instead of just focusing on the hairs, they used stiff fabrics integrated with soft elastomers to replicate the macro draping effect of the gecko's entire toe pad, allowing it to conform to walls and hold significant weight.
Oh, very cool.
But where we see the most dynamic application of this technology right now is in soft robotic grippers on factory floors.
How does a gecko gripper work in a factory setting? What is it replacing?
Think about a traditional industrial robotic arm trying to pick up something fragile, porous, and irregularly shaped. Let's say a raw egg, or a freshly baked pastry, or a delicate piece of curved glass. A traditional mechanical claw requires clamping force, which might easily crush the object. A traditional pneumatic suction cup might not be able to get a proper vacuum seal on a rough or porous surface like a muffin.
That makes sense.
But a gecko-inspired soft gripper doesn't need to squeeze, and it doesn't need air pressure. It can gently drape its pads over the irregular shape, engage millions of synthetic nanocontacts, and lift the object purely through van der Waals forces.
And then to drop it, they just roll the pad back.
Exactly. By simply altering the angle of the pad, it can release the object perfectly cleanly, leaving no sticky adhesive residue or chemical contamination behind.
That is incredibly useful for manufacturing. But earlier in our intro, we mentioned that this technology is bound for the International Space Station. I know NASA is always looking for new tech, but why do aerospace engineers specifically care so much about gecko feet?
NASA cares deeply because the ultimate frontier for this technology is outer space. At the Jet Propulsion Laboratory, robotics researchers have developed something specifically called the Opposed Pad Gecko Adhesive Gripper. Space is arguably the most relentlessly hostile environment imaginable for traditional human engineering.
Okay, I want to explore this. Why can't astronauts just use heavy-duty duct tape or industrial epoxy in space? What goes wrong?
Several catastrophic things go wrong. First, extreme vacuum outgassing.
Outgassing, like it gives off a gas.
Yes, traditional glues and pressure-sensitive tapes rely on liquid solvents and volatile organic compounds to remain sticky and flexible. In the hard vacuum of space, where there is zero atmospheric pressure, those liquid solvents will literally boil away. They outgas.
Wait, they boil?
Yes, this instantly dries out and destroys the adhesive, turning it into useless dust. Furthermore, the outgassed chemicals can float around and contaminate sensitive optical lenses or solar panels on the spacecraft.
Oh, wow. I never considered that glue would boil in space.
It gets worse. The second major problem is embrittlement. Objects in low Earth orbit go through extreme, brutal temperature swings. When a satellite is in direct sunlight, temperatures can soar to hundreds of degrees above zero. When it passes into the Earth's shadow, temperatures instantly plummet to hundreds of degrees below zero.
And plastic tape does not like that.
Traditional polymers and rubbers freeze solid, become incredibly brittle, and simply shatter under stress.
Okay, so tape freezes and shatters and glue boils away. What about just using mechanical claws?
Traditional mechanical grippers have their own severe limitations in space. They usually require the satellite or object to have specific mating features like a predefined handle or a grapple fixture built into it beforehand. If you are trying to catch a piece of smooth space debris, a claw has nothing to grab onto.
Because it's just a smooth metal sphere.
Exactly. And if a claw tries to grab a delicate solar panel, the high squeezing force required to hold it could easily crush and destroy the panel.
This is where the Gecko tech shines. A Gecko adhesive is entirely dry, it's solid state. It doesn't rely on liquid solvents that can boil in a vacuum. It relies on intermolecular atomic forces, which, as we established, work perfectly fine in a vacuum.
They do.
In fact, didn't they prove that exact point way back in 1934 during those early debunking experiments?
They absolutely did. The 1934 vacuum chamber experiment that debunked the suction cup theory proved conclusively that geckos do not need air pressure to stick.
Full circle.
NASA realized that this biological mechanism was the absolute perfect solution for zero gravity and hard vacuum. The JPL-opposed pad gripper uses arrays of synthetic microscopic wedges. When you push the pads against the surface and apply a slight pulling tension, the wedges engage and stick.
And to unstick it.
When you release the tension, they unstick. No liquids, no suction, no temperature-sensitive goo, just pure mechanical quantum adhesion.
So what does this all mean? We have the theory and we have the prototype. Is this just sitting on a desk at JPL, or are there actual gecko robots floating around in space right now?
It is very real and has been actively tested. These grippers have undergone extensive microgravity testing on parabolic flight trajectories, the famous vomit comet airplanes that simulate weightlessness. And more importantly, the technology has been deployed and tested on the International Space Station itself.
What exactly are they doing with it on the ISS?
They've run several successful experiments. They've tested using the grippers to capture floating objects weighing 20 pounds or more. They've even tested using larger gecko adhesive pads to temporarily anchor 250-pound astronauts to the walls of the station.
Wait, really? To the wall?
You have to remember, in zero gravity, if an astronaut tries to turn a wrench to tighten a bolt, Newton's third law dictates that the force will just spin the astronaut around instead. They constantly need to tether and anchor themselves.
Oh, that makes sense.
Gecko adhesives provide a way to create a temporary, incredibly strong, residue-free anchor point anywhere on the smooth interior walls of the station without needing pre-installed handholds.
That is so profoundly practical. Just slap a gecko pad to the hull, click in your tether, and get to work.
Exactly. And looking forward, NASA has ambitious plans for autonomous climbing robots based on this tech. They're developing prototypes like the Lemur 3, which stands for the Limbed Excursion Mechanical Utility Robot.
Lemur 3, I love NASA acronyms.
It is a multi-limbed, spider-like robot equipped with Gecko adhesive feet. It is designed to crawl along the exterior hull of the space station or inspect delicate satellites. Because it uses van der Waals forces, it can walk directly on smooth thermal blankets, glass optical lenses, or fragile solar panels without scratching, crushing, or damaging them.
That is incredible.
In the future, fleets of these robots could perform exterior repairs or even be deployed to gently capture and deorbit dangerous space debris.
Capturing a dead satellite hurtling through orbit with a giant robotic gecko hand. That is undeniably the coolest thing I've heard all week.
It really is the perfect culmination of this entire body of research, taking a 100-million-year-old biological adaptation from a terrestrial lizard running up a tree in the Cretaceous period, reverse engineering its quantum physics, and deploying it to solve engineering problems in the vacuum of Earth's orbit.
Let's just take a moment to summarize this incredible journey we've been on today. We started by zooming in on a microscopic gecko toe, discovering it was covered in a billion tiny, ultra-stiff beta-keratin spatulae. We learned that by sliding just 5 micrometers across a leaf, that toe can bypass the Dahlquist criterion and engage van der Waals forces, harnessing quantum-level atomic attraction to generate enough force to suspend a 290-pound linebacker.
That's a lot to take in.
We saw how the gecko can effortlessly peel its toes back at a 30-degree angle to break those bonds, using the resulting mechanical snap to catapult dirt away and keep its feet perfectly clean without water.
A true mechanical marvel.
And finally, we saw how brilliant human engineers at places like UC Berkeley, Stanford, and NASA JPL are taking those exact principles, contact splitting, directional adhesion, and hierarchical structures, and turning them into dry robotic grippers that are currently catching floating objects on the International Space Station. It really highlights the sheer beauty of interdisciplinary science.
It truly does.
Yeah.
Evolutionary biology, contact mechanics, and material science all merging into one cohesive, awe-inspiring story.
It's a testament to the power of looking closely at the natural world.
And if there is one core insight you take away from this deep dive, let it be this: the next time you're sitting in your living room drinking your coffee and you see a tiny gecko scurrying up your window pane, realize that you aren't just looking at a simple lizard. You are looking at a masterclass in quantum-level physics and advanced mechanical engineering. You are witnessing a technology perfected over 100 million years of brutal natural selection, playing out seamlessly right in front of your eyes.
I can promise you I will definitely never look at a gecko the same way again. But before we sign off, I want to leave you, our listener, with a final, slightly provocative thought to ponder.
Oh, I'm ready for this.
Something that wasn't strictly covered in the academic research we reviewed today, but that feels like the logical, if perhaps science fiction-esque, next step on this timeline. We have spent an incredible amount of time, money, and brain power trying to build synthetic materials, silicon wafers, polyurethanes, carbon nanotubes that mimic the gecko's foot.
Right, trying to copy nature.
But as the fields of genetic engineering and synthetic biology advance at lightning speed, we might be looking at the wrong manufacturing process entirely. Could the future of biomimetics not be about building a plastic gecko gripper for a factory robot, but rather modifying organic human skin?
Okay, now that is an interesting thought.
Could we design living biological suits or even use gene editing to natively grow beta-carotene nanostructures on our own hands and feet? Could humans one day biologically grow our own gecko pads and climb the glass walls of our cities exactly the way nature originally intended?
Now that is a truly fascinating, paradigm-shifting engineering challenge to ponder.
Just a little something to think about while you stare up at the ceiling tonight. Thank you so much for joining us on this deep dive into the sticky quantum world of the gecko foot.
It's been an absolute pleasure exploring this phenomenon with you. Keep questioning the world around you.
Until next time, stay curious.